Next question is the change in potential energy of the system per unit, per mole of gas in the system. Okay, so you should work that out. Okay, well, here it is. You're just going to multiply delta Y by the weight of the water that gets displaced. What's the well, the volume of the water displaced is delta V12 that we saw just previously, and we multiply that by the density of water to get the mass of the water, and then by the acceleration of gravity to get the weight of the water. So we have delta Y times the weight of the water. Now, delta Y, if you recall, was T minus T naught over T naught times P naught over rho G, and the rho G, well, the delta V12 was TF minus T over T times RT naught over P naught, the expressions that we got previously. Again, those expressions probably won't immediately make a lot of sense to you, but you can refer back and see that those were the expressions, and hopefully you derive them yourself so that you have some familiarity with them. And then this change in volume here is multiplied by rho G. The rho G here divides the rho G here, it goes away. We have a P naught here and a P naught here, they divide out. We have a T naught here and a T naught here, they divide out, so we end up with a relatively simple expression, T minus T naught times TF minus T over T multiplied by R. Now, in doing this, we worry about the units of these quantities. Remember, RT over P is like nRT over P, and that would be the volume. It's a unit of volume, so this is a unit of volume. And this is unitless, temperature units in the numerator and the denominator. The rho G is going to divide out. We can make sense of that easily enough. It's the weight per unit volume, and so forth. And I'm not going to go through the P naught over rho G we already talked about. This is units of pressure over units of rho G. Gives you units of distance, and that's our delta Y when we multiply it by this. Okay, well, the units look right here. Do they look right here? Is this, what are the units of this going to be? Well, we have units of temperature here. We have units of temperature in this factor. So what's in this parentheses has units of temperature. What's in this parentheses has units of temperature. The temperature in the denominator, well, the units are going to divide the units of one of those, leaving the other. So we have units of temperature times R. Now, the units of R are joules per mole Kelvin. The units of temperature are Kelvin, so we end up with joules per mole, which is the unit we expect to get if we do potential energy change per mole. Okay. Now, the next question is, what's the ratio of the potential energy change per mole, which we've just seen, to the heat added per mole? Okay. So how are we going to get that? You should work that out, but here we go. Change of potential energy per mole divided by the heat added per mole. Well, you see that the n's cancel out, and we just get change of potential energy over change in Q. Our expression for change in potential energy right here, we just copy it, and we divide that by the energy that we added to raise from T naught to T, using the 5/2 R, because that was done at constant volume, and then from T to TF, which is done at constant pressure, we have the 7/2 R, and that's the energy per mole added at the two different phases. We add those together, we get the total energy per mole. Okay. Now we simplify this expression, and it's fairly easy to simplify. Our numerator is going to contain these two binomials. Our denominator is going to contain the T here, and we have an R here, but we also have an R in the denominator that can be factored out. So the R goes away, and the denominator then just becomes, well, if we multiply through here, we got 5/2 T minus T naught, 7/2 TF minus T. We're going to have 5/2 t minus 7/2 t that we get here is going to give us just a negative t. And then we're just going to have the negative 5/2 t naught, which I put here, and the 7/2 tf, which I put here. So there's the expression. It's not that bad of an expression. Okay, of course, we're going to want to maximize this, which means we're going to have to take the derivative of this expression. And it looks a little bit ugly. You know, it's a derivative that anybody who's had a semester of calculus should be able to do if they keep their wits about them and keep their bookkeeping straight, just using product and quotient rules, not a particularly difficult integral. But to make it even a little simpler, I'm going to expand this numerator, and just multiplying these things out, you can check the expansion, and also multiply through by t in the denominator, and you can check the arithmetic and verify that this expression is correct. Now that's the expression that we're going to proceed to try to maximize. And that gets a little hairy.